All right, so here is a static equilibrium problem. If you need to pause, read, and then keep up, you have 4 parts of A, B, C, D, E. I'll just go ahead and get into it. So you have a rod, you have a mass that's hanging a length of L over 4 away from the farthest end. The pivot is at point P, and then it wants us to find an expression for Py, that the force exerted by the pivot. So let's go ahead and do that. So for part A, the first thing you should do is identify Py. So the floor is going to push up on this particular end of the rod, and that's going to be your normal force. But here we'll just call it Py just because the problem calls it Py in part A. That's essentially what you're asked to do. So in order to find Py, all you have to do is identify all your forces in the y direction, because the system here is static, meaning it's not moving or rotating. So net force has to equal to 0, and also your torque has to equal to 0. So keep those two important concepts in mind as you keep up. All right, so here is the weight of the beam. The weight of the beam is drawn from the center of the beam there. That's going to be pointing downward. And then here you also have the weight of the hanging mass. In this particular problem, the weight of the beam and the hanging mass are both identified as capital M's. So I will just go ahead and call that M times G, and also M times G for the weight of the beam and also the weight of the hanging mass. Okay, so that's it. So essentially, that's all the forces you have in the y direction. You notice here the tension is perfectly horizontal, so therefore that is in the x direction. So that's so yeah, that's it. So I'm just gonna go ahead and set up my Newton's function. Net force equal to ma. But here you notice I am focusing on the y direction just because Py again is in the vertical direction. So I'm just gonna go ahead and write out Py, which is pointing upward, and I want to subtract it from both these vectors pointing downward. So f of g in blue here, f of g in green. It's going to point downward. So you can add a negative if you want, but I like to go ahead and introduce my negative signs right off the bat. So I'm going to say Py, which is positive. I want to subtract it from both these terms, and that's going to equal to 0, because again, this is a static system, meaning Ay is equal to 0, and the mass of the system here doesn't really matter, only because well, whatever mass of the system is times 0 is just going to give you 0 on the right side. So the question essentially asks for Py in part A. So I'm just going to isolate for Py by manipulating this particular function by moving the both of the mg terms, which are negatives, to the right side by adding them. All right. So other than that, really here, if on the right side of the equal sign, you have mg plus mg, which is just 2mg. So I can simplify it down to Py is equal to 2mg, and that is your expression for the first part A. Okay. Let's do B. B wants us to find the expression for T in the cable. So to do this, I'm just going to go ahead and set up my net torque, because I know essentially without the tension, the rod is going to rotate in the clockwise direction. So here you're tying a string just to keep this particular rod, at a diagonal, okay, or a stationary in this current position in the diagram. All right, so T here is going to point leftward. It's going to point towards the wall, or whatever point A here is. And then other than that, I have identified the moment of arm. So to do torque, you need your tension and you need your moment of arm that are perpendicular. So here T is pointing in the leftward direction and the x direction, and then the point of contact is where B is. From P, from the floor all the way to B is the length L, as indicated in the diagram. So here my dash orange line, that's just going to be L sine theta. It's sine because it's opposite. So L being my hypotenuse, and then the vertical leg here, which is L sine theta, is L sine theta because this once again is the opposite leg. I need this leg because y is perpendicular to x. And then likewise, I'm going to do for f of g here. F of g here for the beam is placed at the center of the beam. So from point P to the center of the beam, that's just L over 2. I don't need L over 2 though, because f of g is in the y direction, and the blue line here, that's L over 2, is not in the y direction, or excuse me, it's not in the x direction. So I need L over 2 cosine. So the dash blue line here, this is in the x direction, which is perpendicular to the f of g, or the weight of the beam itself, or the rod, whatever you want to call it, essentially. So that's going to be L over 2 cosine theta. And then likewise here, f of g in green here, that is where the mass is hanging. And the mass here is hanging a distance of L over 4 away from point B. However, it's important that you measure lengths correctly. These values are measured away from the pivot being point P here. So from P to where the mass is hanging, that is a distance of 3/4 L. It's 3/4 because the whole entire length is L. And then here in the diagram, it gives you L over 4, which is 1/4. well, the remaining leg must be 3/4, right? So essentially, if you want to, you can just take L minus L over 4, and that would just give you 3/4 L, and that's where I got the 3/4 L from. But once again, 3/4 L here is not perpendicular to the weight in green of the hanging mass. I need 3/4 L cosine theta because 3 over L cosine theta is in the x direction. The weight of the mass is in the y direction. X and y are perpendicular. So therefore now I have everything, so I'm just going to set it up. All right. So essentially, if you look at the tension in the string, that is going to produce a counterclockwise torque. It's going to cause the beam here to rotate counterclockwise. However, the weight of the beam itself and then the weight of the hanging mass will generate a clockwise torque. So if you can visualize, if you cut the string, the rod here, the beam here, will rotate in the clockwise direction. So the weight of the beam itself and the hanging mass will contribute to the clockwise direction. So in my work here, I have T. I'm going to multiply by L sine theta because these two are perpendicular. And then on the right side, in blue, I have the weight of the beam itself times where the force is placed at the center of mass of the beam, which is L over 2, but I need to do cosine because that's in the x direction. And then likewise, f of g here is in the y direction for the weight of the hanging block. And then 3/4 L cosine theta is the perpendicular leg, which is in the x direction. Other than that, as you can see, both all three terms have an L, so I'm just going to cancel it out. And then here I'm just going to clean up a little bit. You can see that on the right side you have an mg cosine theta, and then on the green you also have an mg3 cosine theta. Both these though have different denominators, so I'm just going to go ahead and clean up a little bit here. So here on the left side, everything really is the same except without the L's because I cancel L out. And I'm just going to find common denominator. Here, 2 and 4, the common denominator is 4. So I'm just going to turn this particular term into 2 over 4 just to get a common denominator. And then as you can see, you have mg times 2 times cosine, and then you have mg times 3 times cosine all over a common denominator 4. So if you want, you can just add 2 plus 3, which is 5, and the common term here is just mg cosine theta, and that sits over a common denominator of 4. Okay, so I just cleaned up a little bit here. So the 5 comes from really just saying there's 2 mg cosine theta plus 3 mg cosine theta, and those are like terms. All right, but we don't have t by itself yet, so here on the left side we just have sine theta. So to get rid of sine theta, we just divide both sides by sine theta. So I'm just going to move sine theta from the top left down to the bottom right to join the 4 there. So essentially here you have an expression for t, which is 5 mg cosine theta divided by 4 sine theta, and that's it. It just wants an expression. It doesn't want us to solve yet. So let's go ahead and move on. Okay. Here in the next one, part C, it wants us to write an expression for the x component, px. Earlier we did py already. Right. The floor here is going to exert a normal force, and then keep in mind that for a system to not move, the net force in the y direction is equal to 0. However, the net force in the x direction must also equal to 0. Otherwise, there's a conflict in these types of problems. All right, so I'm just going to go ahead and redraw my t there. That's pointing left. However, there's only one arrow pointing left, which means I need an arrow pointing right. So I know that point P is exerting some sort of force in the positive direction to keep this particular system from moving horizontally, which I think is common sense here. Right? You have an arrow pointing left. To get 0, you need an arrow pointing right. So Px here is going to be pointing to the right. So essentially, I'm just going to set it up just like part A, where I have net force equal to ma, except here I'm just going to focus on the x direction. And as you can see in my work, there's only 2 arrows. There's a t pointing left, there's a px pointing right. So I'm just going to go ahead and take the right, which is px, subtracted from t, which is pointing leftward, and that's going to equal to 0. All right, so I do positive minus negative here, or it's up to you. You can add a negative if you want. Once again, ax is 0, so the right mass times 0 is just 0. So I'm just going to go ahead and solve px by moving this negative t to the right side. So px is going to equal to the magnitude of t. Essentially, that is the answer for part C. All right. Let's go ahead and do D. D says now, what is the magnitude of the tension? If you're given that the mass of the beam is 32 kilograms, and the length of the beam is 14 meters, and then the angle here is 32. I do want to point out, while the length of the beam is given, if you kept up with the previous, couple of slides, you notice that I cancel L out in my work when I set up torque. So while the while the length of the beam is given, you're really not going to need it. Okay, so I'm just going to use the expression that I derived previously. T is equal to 5 mg cosine theta divided by 4 sine theta. Once again, as you can see in this expression, there is no length involved here. So just because the information is given to you doesn't mean you really need to have to try to incorporate or use it. So don't get suckered into information that you don't necessarily need. All right. So here I'm just gonna plug in M, which is 32, and then G, which is 9.8, and then cosine here at 32 is given. The angle is given here is 32. And likewise on the bottom, the only thing we have to substitute in is just theta. And this is really just plug and chuck now. So I cleaned up on the numerator. I got about 1329.74. And then on the bottom is 2.12. And then here the unit is kilogram times meters per second square, which is the same thing as newtons. So I'm just going to condense kg times meters per second square into newtons, which is the proper unit for force for the tension here. So if you do that on your calculator, you should get about 627.2 newtons. Okay, and that is for this particular problem. All right, I hope that helps. Stay nerdy, don't be wired.